How do mathematicians study infinitely many possible values of a linear operator? Look at this standard matrix. It has 3 distinct data points, eigenvalues. Expanding to an infinite dimensional space, those points smear into a continuous region. We break this region into 3 zones defined by Kreyszig: the point, continuous, and residual spectra. To do this, we need to master a tool called the resolvent set. Before we build that tool, keep 3 properties of our space in mind. We are working in a Banach space, meaning it is complete and has no gaps. Our operators are bounded, meaning they don't stretch vectors to infinity. And we look for dense sets, subsets so closely packed they effectively approximate the entire space. In finite dimensions, we find eigenvalues by setting a determinant to 0. In infinite dimensions, determinants do not exist. We have to abandon that search and build a new diagnostic tool to test our operator. This is our test operator, t sub lambda. Operator t minus lambda times the identity operator. We feed input x in, generating output y. Our test depends on perfectly reversing this. That backward path is the resolvent operator, r sub lambda. In a finite matrix, if an operation is 1-to-1, it is automatically onto. Every output has a unique input, and every possible output can be reached. In infinite dimensions, that rule breaks. An operator can be perfectly 1-to-1, preserving unique inputs, while completely missing large sections of the output space. Because of that friction, we cannot just ask if the resolvent operator exists. We must evaluate its existence, the density of its domain, and its boundedness. Those 3 properties will tell us exactly what kind of spectral value we have. This flowchart starts with any complex number, lambda, passing into our first decision node. The first test is simple. Does the resolvent operator exist? In other words, is our test operator injective? If it fails this first test, the inverse does not exist. That means lambda is a standard eigenvalue, and we place it here, in the point spectrum. If the inverse does exist, we move to the second test. Is the domain of our resolvent dense in the overall space? If the answer is no, it means our inverse can only reach a fractured, incomplete portion of the space. This lambda falls into the residual spectrum. If the domain is dense, we arrive at the final test. Is the resolvent operator bounded? If it is unbounded, meaning it stretches certain inputs infinitely, lambda belongs to the continuous spectrum. If a value passes all 3 tests, the inverse exists, its domain is dense, and it is strictly bounded, then lambda is not a spectral value at all. It drops into the resolvent set, a safe zone where the operator behaves perfectly: point, residual, and continuous. Every complex number that fails to reach the resolvent set will fall into exactly one of these 3 disjoint boxes. Together, they make up the entirety of the infinite dimensional spectrum. Let's test a concrete example: the right shift operator on the sequence space L2. It takes an infinite sequence of numbers, shifts every number 1 position to the right, and drops a 0 into the first slot. We are going to test the value lambda equals 0. Pause the video here. Run lambda equals 0 through the 3 nodes of the flowchart yourself. Node 1. Does the inverse exist for t sub 0? Yes. Shifting a sequence to the right is perfectly reversible if you just shift it back to the left. The inverse is the left shift operator. Node 2. Is the domain of this inverse dense? Look at the highlighted first position here. The right shift operator always leaves a 0 in that first slot. Therefore, the left shift inverse is only defined for sequences that start with a 0. It completely misses any sequence starting with a 1 or a 5. That domain is not dense. Because it fails the second node, lambda equals 0 must belong to the residual spectrum. We have our proof. In infinite dimensions, an operator can perfectly preserve inputs, acting strictly 1-to-1, while failing to cover the output space. If you are working in a complete Banach space, lemma 7.23 provides a structural guarantee. If your original operator is bounded, and the resolvent passes the first 2 nodes, meaning it exists and has a dense domain, the Banach space automatically extends that inverse to the entire space and guarantees it is bounded. Completeness means there are no missing limits. Because the space is solid, a well-behaved operator defined almost everywhere will automatically secure itself everywhere. This math dictates physical reality. In quantum mechanics, the point spectrum maps directly to the discrete, quantized energy states of a bound electron. The continuous spectrum maps to the energy states of free-floating particles, where values are no longer restricted to rigid steps. This table summarizes the shift we have made. Finite matrices only have eigenvalues, and being injective guarantees being surjective. Infinite operators fracture the spectrum into three distinct parts, because being injective no longer guarantees covering the whole space. As you review Chapter 7, commit the disjoint union of these three spectral boxes to memory, and whenever you are faced with a standardized functional analysis question about the residual spectrum, use the right shift operator as your immediate mental counterexample.